So I wanted to end this introduction to circuits and electrical engineering and programming, hardware versus software, by talking a little bit about transistors. You've probably heard of transistors. They're the basic building block of modern electronics. It's a semiconductor device. It's a switches between zeros and ones, and that's the machine language that's used as the basis for programming. Okay, so just switching over here to some notes on what we're talking about. And it all starts with an atom, with silicon. So you've heard of Silicon Valley. What are they talking about? What's so important about silicon? This particular atom has 4 valence electrons, and it would like to have 4 neighbors that it's happily bonded with. If you've taken a little bit of chemistry, you'll remember about those valence electrons. Something interesting can happen if we put these impurities inside of a silicon matrix. So let's say we have all these silicon atoms, they're all happy, and we introduce this guy, boron, and boron only has 3 valence electrons. So 3 protons, 3 electrons. This is how boron's charges are balanced. And if one of these oddball atoms gets put in with all the silicon, what you get is silicon has this 1 electron that's now not bonded to anything. So this is actually called a p-type material. It is not actually positively charged. If you count up the number of protons and electrons, they're balanced in this picture. But it feels positive because it wants another electron. It wants this electron not to balance charges. It wants the electron to balance bonding between the electrons. So that's the key thing here is there's balancing electrons and protons with negative and positive charges, but there's also a balance needed for just bonding the atoms together. So it wants electrons just to satisfy those very strong bonds. Okay, on the other side, this is another guest molecule. So phosphorus has 5 valence electrons. Same thing. So if you look at the protons and electrons and balancing charges for this guy, this is what is going to balance all of its charges. Now, if you put a phosphorus atom in silicon, you get kind of the opposite effect. This is called an N-type material because it has this, and it's not really an extra electron. Charge-wise, if you add up the protons and electrons and look at charges being balanced, so this picture is where the charges are actually balanced, but because this electron is not bonded to anything, it's like it's negatively charged. It's going to give up a negative electron here. So if you put this p-type and n-type material together, you can maybe guess what will happen. This extra electron that's not bonded is going to get pulled over to this other side just to satisfy the bonds of this thing. Now, something interesting happens when that electron gets pulled over. Now the bonding is happy, but charges are imbalanced. So you now have extra electrons, and the p-type material becomes negatively charged. It has too many electrons over here. And the n-type material is now missing a charge. So it is now positively charged because it doesn't have enough electrons to balance the protons that are in these atoms. So you get this kind of barrier between the materials with a positive and a negative side. And what you're looking at right here is 2/3 of a transistor or a diode. This is actually a one-way valve for electrons. You've heard of light-emitting diodes, and when you use an LED, you have an anode and cathode. You have to get those legs in there right. Okay, so how this works, if I supply electrons to the n-type material, so this is remember, it's lost its electrons here. It has some positive holes. So the electrons, negative attract to positive, and everything is happy, and it will flow through this direction. If I try to put electrons into the other side, negative repels negative, and it can't go through. So it's essentially a one-way valve for electrons. It can travel one way, but it cannot travel the other way. So diode versus a transistor. What happens with a transistor is you're going to put that P-type material. You can either have an NPN or PNP. It works either way. But what we're going to do is we're going to have like two diodes sandwiched together. And at first, this seems pretty silly because now the current can't go either way. So it's repelled coming in one way, it's repelled coming in another way, and it cannot get past this wall of negative charges. Transistor has 3 wires coming out of it. Let me just show you a picture of these guys. This is a very large one. We have a collector, a base, and an emitter. These 3 wires connect to these 3 areas in that NPN junction. And what happens is there's nothing coming into the base. So if the center wire is not connected to anything, current cannot flow through this thing. Okay, it can't go this way, negative versus negative, can't go this way, negative versus negative. So if it was a switch, and that is what a transistor is, it's like a switch. So the switch is off if nothing is coming into the center base wire. But if you put something into that wire, now we've pulled off the electrons on this depletion zone. You no longer have a big wall of negative charges. And so if you just pull away those extra electrons, now you can get from one side of the circuit to the other. So it's a switch that either allows current to flow through it or does not allow current to flow through it. But it doesn't have any mechanical moving parts. Like your light switch, you actually touch 2 wires together to get the current to flow through those 2 wires. Versus this one, you're not actually moving those wires to touch one another. You're opening up flow or not opening up just based on a current. So you can use an electrical signal to turn on and off an electrical signal with no mechanical moving parts. On, off, 0, 1, a switch with no moving parts. So binary is the language of computers, and I wanted to do a few just very simple circuits to create zeros and ones, on or off, high, low. It's not actually a 0 or 1, it's just, is there current flowing through it or is there not current flowing through it? And that information, 0 and 1, combinations of zeros and ones turn into information that your computer stores. Okay, so this is the symbol for a transistor. You can see there's 3 legs. The base, that is what is coming in to the center. And depending on what's coming into the base, that's going to determine if the collector and the emitter are connected or not. So in a traditional switch, you would just touch 2 wires together. It would be like touching the emitter to the collector together. But for this one, you're not actually moving those wires to touch one another. You're just putting a signal into this center base. The symbol in a wiring diagram for a transistor, you can see there's an arrow. It's not actually perfectly symmetrical in here, so there is a direction that the current would like to flow through. It would like to come in on the collector side, go out the emitter side. If there is nothing coming into the base, then nothing gets through from the collector to the emitter. If there is a signal coming into the base, it pulls all those electrons off, there's no more depletion zone, then the collector is connected to the emitter. So off, on, based on what's coming in here. what you can do is create what's called a truth table. The truth table looks at what's coming into the circuit. So this is what's coming into the base, into this third little wire here. And depending on what's coming into the base, you will then see what's coming out of this circuit. And we can represent the output with an LED. So that LED is just going to show us if there's current flowing through it or not. The emitter follower gate is the first one that we will build, and it shows how the switch works. We'll then go to some more complicated logic gates showing combinations of inputs to create a different output. So logic gates are created from multiple transistors that are wired together. So this would be the symbol for an OR gate. And for those OR gates, we now have two transistors. We have A, and this is the base going into A, and here's B, the base going into B. And depending on what's happening in these two inputs, we will get either a 0 or a 1 on the output. Okay, but before we get into more complicated circuits, start with just this emitter follower gate. Popping over to the lab, there's a description of what emitter follower is. There's a wiring diagram showing we have a positive 6 volts being fed into the collector. We have another voltage coming into the base, and our output is going to be determined by what is coming out of the emitter here. So the input is what is coming into the base, and the output is represented by this LED here. So let's go ahead and wire this together in Tinkercad and then fill in this truth table. And we're then going to take a picture of what you made in Tinkercad and paste it in here too. So that's all you have to do is fill in the truth table and put the circuit in here. So I have my screen split here so that we can see that wiring diagram and build something over here. So I'm going to grab a power supply. Let's see, 6 volts, 9 volts. It doesn't actually matter how much. So I'll just go ahead and grab this 9-volt battery. And maybe to just keep this simple, rather than using a breadboard, I will just wire this straight together. So I need a couple of resistors, I need an LED, and I need a transistor. Here's an NPN transistor. And if I hover over this, I can see there's a collector. So that's going to be this wire right here is the collector. I have a base, that's this input that goes into it. This controls if these two wires are attached together, and then the emitter is what's going to come through this LED out to ground. Okay, so if I follow this wiring diagram, maybe I'll put this collector on the top just like it is up here. So I want to put some kind of a voltage into my collector, and I want to see if that will be able to travel through the transistor and back out of the emitter. So through the emitter, and that will go through a, so we'll say 4.7 kilo ohm. And remember, for an LED, there's an anode and a cathode. The anode needs to go to kind of the positive side of this, and then the cathode is the little piece that will go to ground. So we'll say that this is the ground side of our circuit. Now, if there's nothing coming into the base, if I start this simulation right now, the LED is not turning on. So that means the current is not able to flow from the collector to the emitter. And what that means in terms of our truth table over here is that if I have a 0 coming in to my base, I have 0 going out to my output. So I can maybe grab a screenshot showing that my simulation is on, my output is 0 because my input is 0. So let me just grab this snip, and I could just write a note on here that 0 coming in is 0 going out. So this is my snapshot, edit copy, edit paste, showing one of those states. I now want to try the other state for turning this thing on, and that is going to involve putting something into my base. So I've got a 10 kiloohm. I don't need to put too much in. It doesn't take much, but I can click on my resistor, change that to 10 kiloohms. So we'll follow this wiring diagram here. I'm going to turn this around, attach that to the base, and let's wire both of these now, just so you can see better what's happening. So I have the positive volt coming into the collector, and then I'm also going to have a positive volt coming into the base. So that signal is going through the top and it's going through the base. So now if I start my simulation, you can see that my LED is in fact turning on and off. Maybe I should change the color of that so that it shows up a little bit more, green show up more. There we go. Okay, so the point of all of this is I have turned that LED on or off, not by actually touching the collector to the emitter, so I'm not actually touching those wires together. I'm turning them on or off with a current. So this is what's going into my transistor, and this is representing what's coming out of my transistor. Okay, so once you study how one of these switches work, the next step is adding multiple transistors together and understanding some of the simple logic gates, and that's the beginning of machine language and binary and all of the stuff that modern electronics uses for programs and controlling things. Okay, so this is what I would like you to do, is to study the wiring diagram, create the circuits, and then as you create those circuits, you're then going to fill in the truth table. So input, what is coming into the transistor, versus the output, what that LED is showing. So the next one, there's an OR gate, and that OR gate is going to have two transistors, two inputs, so A and B, and the combination of what's happening in these two transistors will then be something different coming out of this output transistor. Here's another configuration. So again, we have two transistors, input into the first transistor, so this is A, input into the second transistor, that's B, and depending on what A and B are doing, you will either have this output, we'll call this is our Q, this will either be on or off depending on what's coming in here. So look at nothing and nothing versus maybe there's just a signal coming through B versus just a signal coming from A. what would be needed here to turn this LED on or off? What combination of inputs is going to turn our output on or off? And here's another one. The NOT gate is kind of interesting. So it's a single transistor, but how we're collecting that output is a little bit different. So study this wiring diagram. Let me know if what's happening on the wiring diagram is not really translating. So these little squiggly marks, that is a resistor. So you have these resistors. The resistor has two wires coming out of it, right? And on this wiring diagram, this is showing what those are connected to. So this is connected to an LED and to the transistor. That same wire is going to get connected to two different things here. And then this is the wire coming into the base and going to ground. Okay, so see if you can get through these circuits and see just kind of the very start of how transistors are. Watch some of those YouTubes explaining how computers are made and those CPUs and what's on there. It's a bunch of transistors and a little bit of how machine language works. But these are, really neat little guys, and hopefully this will be an interesting lab that will get, and it's just an introduction, right? So there's, this gets really complicated, and there's billions of transistors wired together on a CPU, and hopefully seeing some of these very simple logic gates gives you a starting of an understanding of just how incredible computers are and what is needed to make this information age a reality.